Alright, what's up everyone? Welcome back to Structure Free Learning, and in this video we continue our moment area method examples to calculate slopes and deflections. And in this problem we've got a cantilever beam, concentrated moment applied at point B, concentrated force applied at point C, and we want to find the slope and deflection at point B, which is right here at the mid-span of the length of this cantilever, and the vertical deflection at point C here, which I labeled VC. And here are the two moment area theorems. The first one showing that the change in slope between 2 points is equal to the area under the curvature diagram, and the second moment area theorem, which shows that the vertical deflection to point B from the tangent line at A is the first moment of area of the curvature diagram. Alright, so let's go ahead and get to it. The first thing I want to do is some basic statics and calculate reactions and draw the shear and moment diagram of this structure. Here I'm going to label the reactions at A, and I'm going to use my equilibrium equations to solve for those reactions, and that's a pretty straightforward process. So if I do some of the forces in the vertical direction, then I'm going to have AY minus 6 kilonewtons equal to 0. And that tells me AY is 6 kilonewtons upwards. If I do some of the forces in the horizontal, I'm not even going to write that out. That's going to tell me AX is equal to 0. If I take moments about point A, I will have minus 18 kilonewton meters minus 6 kilonewtons times 6 meters equal to 0. And that will tell me that MA is equal to 54 kilonewton meters going counterclockwise. Alright, so hopefully you were able to do that, and if you can do that, and if engineering were McDonald's, shoot, right now you'd be a small fry, right? And what we want to do is become Big Macs, yo. Alright, but seriously, if you need a review on statics, go back and review it. Do some more statics problems and calculate reactions. The next thing that we want to do is draw the shear and moment diagrams, which is again more statics and more mechanics of materials. And for my shear diagram, I just go up 6 kilonewtons, and there's no other concentrated load on this, so it's just straight across 6 kilonewtons. Now for my moment diagram, I start at 54 kilonewton meters here, and then I want to note where this concentrated moment is. This area is going to be my change. These distances were 3 meters and 3 meters each, and so my area here is 18 kilonewton meters, which will take me to 36. And then I have a concentrated moment, which is going to bump me up another 18. And I'll put that over here, and here, this, boom. That'll be negative. Oh, all these are negative. Okay. That's what my moment diagram looks like. And I end at 0 because this area right here is also 18 kilonewton meters. And so that means I'm going to go from negative 18 to 0. And there's my shear and moment diagrams. Now the next thing we want to do is come up with a curvature diagram. But the curvature diagram in this problem is going to have the same shape as the moment diagram, because here we're going to say that EI is constant. And so it's like just taking this moment and dividing by EI. This curvature diagram is all divided by EI. So all these numbers are going to be divided by EI. This is our curvature diagram right here. So now that we have the curvature diagram for the moment diagram, the next thing I like to do is try to draw at least a qualitative displaced shape of the structure. And I know from the moment diagram, from each of these things, I know that this is going to be concave down and concave down on both. And so if I obey the boundary conditions and I draw this deflected shape to match the way that a moment diagram is, I should get a sense of what the qualitative deflected shape looks like. Now drawing this qualitative deflected shape is not always easy, especially when the loading is complicated, and it's something it takes a lot of practice, and you gotta see different types of structures and loadings over and over and over again until you get good at it. So it's what people like to say, you got to do practice, right? It's all about practice. So I start off with the undeflected shape, and now I can draw, or at least based on my moment diagram, and the boundary conditions, I can draw what I think my deflected shape will look like. And I know that at the support here, I have to have a slope of 0, so I'm going to start off horizontal here, and then it has to be concave down, going all the way across. When you analyze a cantilever beam using the moment area method, you really want to be able to know some slope or deflection at some point, and boundary conditions are really good places for this, especially in the cantilever beam, because here at the fixed support, you know, the slope is 0 and the deflection at that point is 0. So this point A in our problem is a good reference for us to find the slopes and deflections at any other point along the length of the cantilever. So the next thing I want to do now is go ahead and calculate the slope at point B, which I'll label theta B here. You know, what I like to do is draw the tangent line where I want the slope. So here, the tangent line at point B, and that angle with respect to the horizontal, that is theta at B. That's the slope at B from the horizontal. And what I can do is, because I know the tangent line at A is 0, the tangent line at A here is just straight across. Bam. If I calculate the change in slope from point A to point B, then that's going to be my slope at point B, right? So here, theta B is equal to theta B with respect to A, just because the slope at A is 0, which is the same as calculating the integral from 0 to 3 meters of the curvature diagram EI times dx. I'm not going to try to come up with a function for this line from 0 to 3 meters. It's just straight up, I can look at the geometry of the moment diagram. The geometry is simple enough where I can just look at the shape and calculate it. And the area under the curvature diagram is this right here. This area represents the change in slope from point A to point B. And I can calculate that pretty easily here. I could just say that the area of the trapezoid is equal to 1/2 the average of the two uneven sides, which is minus 54 kilonewton meter over EI plus negative 36 kilonewton meter over EI, times the width, which is 3 meters. If I work out the math, this will be minus 135 kilonewton meter squared over EI. And notice EI has units also of kilonewton meter squared, so what you're going to end up with is this theta in radians if you had numbers for E and I. The negative means that we went clockwise from the tangent at A to the tangent at B. It doesn't necessarily mean that the slope is negative, but in this case here, the slope at point B is negative because our structure, or our beam at this point, at point B here, has a slope in this, I guess, downward slope, if you will. And according to this plus V and plus X axis, this is a negative slope. The final result for the slope at point B is equal to minus 135 over EI kilonewton meter squared. Alright, now I want to calculate deflection at point C. And what I've done here is I've drawn the qualitative deflection diagram, and I've redrawn the curvature diagram over here. And the first thing I want to do is draw the tangent lines from my reference, which I'm going to choose point A, and the tangent line at point C. And according to the second moment area theorem, the vertical deviation, or the vertical distance from the tangent line at A to point C, is equal to the first moment of area about point C. And this TCA would represent this distance from the tangent line at A to point C. Now I'm not going to obviously try to find the function and integrate and all that. I can just straight up calculate the moments of error. I can break this up into segments of areas that are nice and convenient for me, and then just solve for the first moments of error. So when I break this up, I'm going to break up this moment diagram into triangles and rectangles. So here is one triangle, here is the rectangle, and then here's my other triangle. So I'm going to call this area 1, area 2, and area 3 over here. And I want to take moments of these areas about point C. So what I need to know is the centroids of each of these areas to point C. And so here, this distance, I'm going to call this x bar 3. There's x bar 1, and the centroid of area 2. You know, this first moment of area is not anything new. You've been doing this since you learned how to calculate centroids of shape. And then in mechanics of materials, if you remember the shear formula, there was this capital Q, which was the first moment of area. And so really, you know, another way to look at this is just the sum of AI times x bar I, right? It's just a summation of this first moment of area. If I go through one by one, this vertical deviation is equal to the area of this first, or area 1, and if you note, this distance right here is 36 over EI. That makes this distance over here 18 over EI. And so the area here of the triangle is 1/2 minus 18 over EI times width times the arm, this x bar 1, and the centroid of a triangle is 1/3 from the fat side, so this would be, this distance right here is 2 meters, which makes x bar 1 2 meters plus 3 meters, which is 5 meters. So this is, the arm is 5 meters. Then I want to add the area 2, which is the area of this rectangle, which is base times height. And then again, times the distance here. In this case, the center is half the distance of 3. So 1.5 plus 3 meters plus 3, which is 4.5 meters. Plus the third area, which is 1/2 minus 18 over EI times the base, which also was 3 meters. And then the distance from point C to the centroid of that area, which is 2/3. From the skinny side, or the thin side, which is 2/3 times 3 is 2 meters. And now I just add all this up right here, and this becomes negative 675 over EI kilonewton meter cubed. And again, you recall that this EI is kilonewton meter squared, so you're going to end up with units of meters. Now the negative doesn't necessarily mean that the deflection is downwards here. What it means is that the point C is below the tangent line at A. And then we'd have to go look at how we established our coordinate system. Here we said this is plus V and this is plus X, and it happens that in this problem that the deflection at point C is equal to negative 675 kilonewton meter cubed divided by EI. And negative because in this case it's negative because it's below the x-axis that we defined. So hopefully this video added some more dimensions to your understanding of the moment area method. Let me know if you have any more questions on the comments below. Alrighty, take it easy. See ya.